Hello and welcome. Today we're going to talk about phase diagrams and bifurcations. So this topic is under the umbrella of what I would call qualitative analysis of DEs. So we know in qualitative analysis of DEs, we've already have one tool under in our front pocket that we use a lot, and that's the slope field. And that's the perfect spot to start to understand phase diagrams because they're very much related. So in a slope field, let's recall that we have some sort of dx dt is equal to f of t comma x. This is the kind of differential equation we're looking at. Okay, where x is some state variable. A state variable, or what you call a dependent variable. And of course, t is the independent. Variable. Okay, so if t is the independent variable and x is the state variable or the dependent variable, and we have this sort of thing, and so basically this function, which is given, and it defines the dE. If we know it, we know that we can draw these slope fields like so, where we have time on the horizontal axis and our state variable x is going to be on the vertical axis, like so. And let's just give an example very quickly. If we have dx dt is equal to 2x. Okay, so at the point 1, 1, of course, the slope is going to be 2. So we can write that there. And we think of that as like, well, we want it to have a slope of 2. So that's about a slope of 2. And now let's look, though. Now if I go up here to x equals 2, of course, it's going to have a slope of 4. And then 3 halves, or sorry, 6, and then so on and so forth, going up. All right, and then at the point x equals half, of course, we have a slope of 1, like so. All right, so one thing you notice, though, is that if I look all at this column, if you will, for that value of t equals 1 and t equals 2, these are, of course, all of these columns here are all the same. And they're the same because this is what we call an autonomous differential equation. An autonomous differential equation is actually of the form dx dt is equal to f of x. And what I mean there is that there's no t in there. And so basically, for any value of t, you get the same exact slope field. So really, it's sort of redundant information. Okay, we still like to draw these slope fields as two-dimensional graphs because, of course, we can, as time goes forward, we can trace a solution through the tx plane. So the slope field definitely has its tool. But really, all the information of the slope field is contained in one column for one fixed value of t. Once we know that column, we know everything. We just have to stack up all those columns to get a picture of the slope field. Okay, so it turns out in the case of an autonomous DE, one that doesn't depend on time in the differential equation right there, if that's the case, then we could study things which we call phase diagrams. So let's now talk about a phase diagram. So a phase diagram and depicts the sine of dx dt at every point x for autonomous DEs. Okay, so let's think of this, an autonomous DE. So again, we'll go back to our example, dx dt equals 2x. And what we're going to do, so in the slope field, we usually write our x on the vertical axis, but with phase diagrams, it's more common actually to go horizontal. So we'll do a horizontal phase diagram like that. And this will be the x domain. And because our differential equation doesn't have an explicit time dependence, what we do is we'll just, all it is a one-dimensional line. So now we have to just indicate that it depicts or indicates the sign. So of course here, so we can see it immediately that if x is positive, then dx dt is also positive. So what we do to depict, what do we mean by depict the sign? So what we actually do is put an arrow going in the right-hand direction for all values of x that are positive. All right. Now, if x is less than 0, then we know that dx dt is less than 0. And so for this whole half of the line, we'll put arrow symbols going the other way, indicating that, so essentially this indicates oops, sorry guys, this always happens. My butterfingers. It indicates the direction that x of t evolves to as time goes forward. Okay, so this simple phase diagram tells you a lot of information about the system. And so one way to understand it is that if you were to have an initial condition, if you were to start at an x naught that was here, I would know that by starting at that initial condition, I know which way I'm headed. I know which way x of t is going. But if I start at a point here, let's say, if I have a negative initial condition, I know that I'm going to go in the negative direction. All right, so that's how we understand the system, is basically as how the autonomous differential equation will evolve or dynamically change given an initial condition. Okay, so the next question then, of course, is what about x equals 0? Well, we know that dx dt is equal to 0 when x is equal to 0. Okay, and that means, of course, that x of t, the solution, is going to be the 0 function. So in this case, right here, when we have the case of dx dt is equal to 0, we call that an equilibrium point. Or actually, we call it a critical point. We also could call it an equilibrium point. Okay, and it's a point where, and what we mean by this, the equilibrium point or critical point, it's if my initial condition x naught is equal to my xc critical point, then we know that x of t is going to be x of 0. It'll be defined as the constant function x of 0. Okay. And so they're the points, of course, where there's no change. And they typically represent sort of boundaries of the system. And what do I mean by that, by boundaries of the system? We see that that point right there, I'm going to put a dot there just to describe it, separates x equals 0 separates two different behaviors, really. One is going right and increasing, and the other is, of course, decreasing, going into the left. And that equilibrium is what divides those two behaviors. Because if I start here, essentially I'm still going in the same direction. In fact, if I start here, I'm eventually going to get to there. So wherever you start, you're just going to pass through all those states going to the left. And likewise on the right. The dividing point between them is that equilibrium. And so we see that we now learn something about systems, and now we have a language to talk about these incredibly important points. And we have there's a whole nomenclature and vocabulary, if you will, to talk about those things. All right, so let's now try some other examples to understand what we want to do. Okay, so let's now talk about, again, let's go revisit the, sorry, I need to readjust my slide again. I keep messing that up. So I'm going to revisit the logistic equation. Or I should say the logistic dE. Okay, let's write that down. That's dx dt is equal to kappa times x of L minus x. All right, and to keep it simple, I'm going to say kappa is equal to 1, L is equal to 1, just to keep things simple. Okay, and so what we have there, of course, is x 1 minus x. So so kind of a step-by-step, procedure for drawing phase diagrams. I did it again. Sorry, guys. I keep trying to not do that, but it's so sensitive. For drawing phase diagrams is as follows. First of all, we find our dE, f of x is equal to dx dt. All right, so again, it has to be autonomous. It can't be time dependent over here. And then what you do is you find all critical points. And that is, i.e., points xc such that f of xc is equal to 0. All right, so let's go look at our example here. We have x, so minus x, or x times 1 minus x. That's our f of x that defines our differential equation. And we want to set that equal to 0. And then clearly quickly we find that if you want to call it x1 or xc1 is going to be 0. And xc2, the other critical point, is going to be 1. All right. And so what we do then is we're going to draw our phase diagram again as a line like that. We're going to put a 0 there. And over here, I'm going to put a 1. Okay, and now I'm going to, now those are my points that represent those boundaries between various boundaries for our system. And the second step then is to discover what sign is between, or I should say what sign dx dt is between critical points. Okay, so the question then is, okay, what's the value here? So I want to find out what the value is here, here, and here. Okay, so let's look at this equation here. We see that if now you can pick a sample point or anything, just look at this thing really quick. If I take, say, the point 1/2, so 1/2, I want to find out what happens at 1/2. I've got 1/2 minus 1/2, and that's going to be 1/4, and that's positive. So we actually say here that that dx dt here is positive. So what we do is we put right-hand arrows going this way, like so. All right, now if I go to a bigger number, if I go to a number bigger than 1, let's say if you were to go to like 10, of course I'm going to get 10 times 1 minus 10, which is going to be minus 9, so you get 90. So clearly things that are above 1 are going to be negative valued dx dt. So any value, any initial condition that starts above 1, of course, is going to shrink going towards 1. Now, if you go to values below 0, what you see is, again, the same sort of scenario. Although this factor of the dE will be positive, this one will be negative, so a negative and a positive make a negative. So we're going to get dynamics that are heading in the negative direction. Okay. So the next thing you want to do then is then identify the stability of critical points. So I haven't talked about stability, but stability is fairly simple. What it means is that stability occurs when arrows point in to a point of interest, like that. So of course we're going to call that point. I'm going to use a solid dot there to indicate that's stable. And then what we say is anything else is unstable. Okay, so what we'll do is we'll put an open circle there. So, so stability is generally thought of as the arrows pointing in, but I need to put a little asterisk there and say not quite. I'm being a little cavalier when I say that. So let's just write that in there. I'm going to put unstable there. So that would be right here, right now, this would be an acceptable phase diagram. It indicates everything you need to know about what the differential equation does to initial conditions. So if I start here, I know I'm going to be going towards 1. If I start down here, I'm going to be going up towards 1. But if I start below 0, I'm just going to go down, and I'll go off to negative infinity eventually as time goes forward. So, so this right here represents a quality phase diagram. But I want to just elaborate before we stop. I want to elaborate a bit more about a little bit more about the definition of stability, because we actually have a more formal definition. There can be cases where the arrows appear to go in towards a equilibrium point, but they go too slowly to ensure stability, or to be defined as stability. So what I want to do is now talk about that. So another piece of vocabulary here is that of stability. So again, we have dx dt is equal to f of x. So stability is a property of a critical point. xc. So again, this critical point, by definition, f of xc is equal to 0. Stability requires Also that the partial derivative of f with respect to x evaluated at xc has to be negative. Okay, so this guarantees then that that we get stability. So let's see an example of that kind of situation. So again, I can have a dx dt is equal to negative x. So here's an example where that is f of x. Okay. All right. So clearly, xc in this case is 0, and the partial derivative with respect to x is equal to negative 1. And that, of course, is less than 0. So so what we say then is that xc is a stable point. That's what we conclude from it. All right. And if I draw the phase diagram, of course, what we're going to get is this. There's our 0, and I put a solid dot there for xc equals 0, and the arrows go in. Great. All right, now let's look at another example. Now let's try dx dt is equal to negative x squared. All right, so just like before, we have xc is equal to 0 is a critical point. Okay, and now let's look at, so f of x is equal to negative x squared, and the partial derivative, or the derivative, I should say, with respect to x is going to be negative 2x. All right, so now what we need to do, of course, is evaluate at xc, which is going to be negative 2 times 0 is equal to 0. Well, 0 is not less than 0. So we actually need df dx evaluated at xc to be less than 0, not equal to 0. So, but now let's draw the phase diagram. So here's our equilibrium. Oh, sorry, I shouldn't draw that solid dot. We see if I go above that, I get a negative value. Now if I go below that, I see I get a positive value. So the arrows seem to be pointing in. So it appears stable. But you notice that dx dt is equal to negative x squared. So for x very small, x squared is even smaller. So what we're getting is basically the differential equation, the rate of change is so slow. So all around here is slow. So while there is motion going this direction towards our equilibrium point, it's so exceedingly slow that it takes a very, very, very long time to actually reach the equilibrium. And so while the motion is traveling that direction, it's not going sufficiently fast to qualify as what we're going to define as stable. Okay, so what we do is we'll put we put that open circle there. We'll say it's quasi-stable, or we're going to need more information to know if it's stable. Okay, let's go try yet another example to kind of see. Oh, I think I made a mistake. So what we see here, I made a big mistake here. I'm very sorry. The phase diagram actually goes negative everywhere. So what we get is it goes towards 0 for x greater than 0, but it goes away for x less than 0. And so it doesn't even appear stable. It's what we call quasi-stable, but what we really just say is that it's stable. Okay, so I hope that clarifies. I'm sorry I had a little trip up with my thinking there. Um, uh, so I hope that clarifies things. Okay, so in the next video, or rather in the last little bit here, now I'm going to talk about a little bit about bifurcations. So bifurcations, and I'm just going to do a simple example of a bifurcation. And in later videos, I'll give you more information and more examples. So, so commonly, DEs have parameters. For instance, here's an example. We have dx dt. We have some sort of maybe exponential decay. So we're going to have some negative kx. All right. So this is some sort of a decay type differential equation where k is a parameter. Okay. And so this parameter might be it might represent some physical property, physical or material property, or material property, or something that might be determined by an experiment. But whatever it is, if you think of it as basically this is actually a family of DEs, one for each k value. Okay, so this k value, then what we can actually do now is draw. So what we want to do is actually examine stability diagrams as a function of the parameter. Okay, so what we can do here, now I'm going to do this differential equation here. So what I might want to do is actually, what I'm going to do is I'm going to put my phase diagrams now vertically. And what I'm going to do is I'm going to draw on this axis now k, different values of k. And so what I might want to do is try, and what I'm going to do is kind of draw a bunch of stacked phase diagrams. And I'm going to represent them vertically like this. One for each k value. I'm going to say that's the k equals 0 value. And I'll see that's the x equals 0 value. Because we see for all these differential equations, xc is 0. The critical point is 0, right? And I want to know what happens. So for k greater than 0, if I go this way, I see that we have stability, that we have decay, exponential decay towards our critical point. So, and then for any k value that's positive, because there's a negative sign associated with it, no matter what the value is, as long as it's positive, we always get stability. So what I can do is actually draw kind of a dark solid line indicating that there is stability for k positive. All right, and then all of a sudden here, I can kind of draw like more of an open thing. And I can draw the arrows now going away here. And I'll draw an open thing there. So here, what you get at k equals 0, of course, is nothing. There's no arrow in any direction. But all the phase diagrams to the left now are going to have an unstable pattern. They all have arrows pointing away from my equilibrium. All right. So this is what I call a bifurcation diagram. You can call, there's many ways to discuss this or render this, but the idea is that if you stack a bunch of phase diagrams up as a function of a parameter, then you can examine how K determines stability. So K can change stability. And K equals 0 is what they call the bifurcation point. And that's the point where stability changes. So K equals 0 is the bifurcation point. Okay, so in later videos I'll explain more and give more example of bifurcations, but now you have a nice definition. Okay, thank you very much.